This is page 2 of the Matrices packet, and we are going to continue solving systems and see what the different cases are for three-dimensional systems. In video 1, we found that we solved a three-dimensional system and got one solution, and it is a consistent independent. And we know that because we got a distinct value of x, y, and z. So this next example is a little different. It has three equations, so it looks fine to start with, and then I'm going to take them and try to eliminate some variables from one variable from at least come up with two equations that has the same variable eliminated from both of them. So the z's look particularly friendly in this setup here. And I'm noticing that if I take equation 1 and 3 and add them together, that the z's will eliminate. So I'm going to write that that's what I'm doing. And when I do 1 and 3, I get 2x plus x is 3x. And y plus negative 4y is negative 3y. And negative z plus positive z eliminates. And negative 2 plus 1 equals negative 1. And the reason I didn't have to multiply by anything first is because the z is eliminated without any multiplication by a common factor like I did on the previous problem. So if I want to get the z's to eliminate again, it looks like these two here, the second and the third, would be a good choice. Because again, the z's will eliminate. So the second and the third, x plus x is 2x. 2y and a negative 4y is a negative 2y. And the z's eliminate. And negative 9 plus 1 is negative 8. So now I have a two-variable system, and I'm going to go solve that. You might recognize right away here that there's definitely a problem, because if you imagined what the slope of these lines would be, I think they're the same. But if you didn't notice that and you were just kind of going along with this, then you would want to continue trying to just solve this by elimination. So it looks like maybe changing them so that the 3's and 2's become 6's. So if I take the first equation and multiply it by everything in it by 2, then I would get 6x minus 6y equals negative 2. And if I take the second equation and multiply everything in that by negative 3, then I will get negative 6x, which is good because then the x's eliminate, but then positive 6y, which means the y's also eliminate, and then that is the source of the problem. So now when I add them together, the negative 6x and negative 6x eliminates, and negative 6y, positive 6y eliminate, and negative 2 plus 24 gives me a number that is not 0. So this is 0, and this is 0, and this is not 0. So 0 does not equal 22. So false, which means no solution. And then if I was going to pick the right words from the beginning of the notes, a no solution is an inconsistent system. So false, no solution, inconsistent. All right, so that's example 2. Then example 3, if we go through and eliminate, say, the x's on this one, I have here in my notes that when you eliminate the x's that you could get y plus 3z equals 7 and 3y plus 9z equals 21. And I'm not going to include the steps to get to that, and only because I think the video will get too long. So if you just say multiply the top equation here by -2 and combine these together, that's probably one of these equations, but I'm not exactly sure. I can't remember now exactly what I did to get that system. But then from there, if we eliminate, say, the y's by multiplying the top equation by -3, then I would get -3y plus 9z, no, minus 9z, minus 21. And the second equation is 3y plus 9z equals 21. And you can tell that then when you combine those together by addition, that you get 0 equals 0, which is true. So there are infinite solutions. And I would say it is a consistent dependent. Now, you're not exactly done yet because there are infinite solutions, but it's not that every point is a solution to the system. It's that probably all the points that are on a line like this are a solution to the system, or perhaps all the points on one plane, but it's not every single point in space. And so there is a way that you are supposed to write your answers to an equation like this. So you want to take one equation, like this one. I can solve it for y. So if I take y equals, this will become -3z plus 7. And then I know an expression for what y is equal to in terms of z. And then I want an equation for what x is equal to in terms of z. So I'm going to take this first equation, x, I don't know, but y I can substitute in -3z plus 7, and then minus z equals 8. And then I'm going to solve that and get x plus 6z minus 14 minus z equals 8. And then I'm going to solve that for z. So this is x plus 5z equals 22. And so x equals -5z plus 22. So one way to express the set of solutions to this problem would be to take, sorry, I'm running out of room here, but to take the x's are equal to -5z plus 22. The y's are equal to -3z plus 7, and they're all in terms of z. So if you pick any number you want to be z, then this is how you can find the x's and the y's that will make all three of these equations true. So there isn't one solution, there's a whole bunch of solutions. And this didn't have to be written in terms of z. It could have been, you could have found all of the equations in terms of x. So you could have had an x here and then equations of x. But it's not quite enough to say that there are infinite solutions, implying that every point is a solution. There are infinite solutions that are of this form. All right, so now we're going to introduce the concept of a matrix or matrices. And they are a tool, one thing they're used for is a tool to solve a system of equations. And it's just an array of numbers such that there are rows and columns, and each element of the matrix has a little subscript here where the first digit of the subscript is the row number and the second is the column number. So if you had, say, A12, A sub 12, that 1, or A sub 1, 2, that 1 indicates that this element is in row 1 and column 2, or row I and column J. When you are solving a matrix or working with a matrix, it's okay to switch any two rows. You can replace a row by a non-zero multiple of that row without changing the value of the matrix, I guess we could say. Or you can replace a row by the sum of that row and a constant non-zero multiple of some other row. So those are a little hard to get used to, and we're going to kind of deal with them by example here. So if I were going to write a matrix to represent this system, I would take the coefficients of these values. Since this is x, it's got a coefficient of 1, then a negative 2, and then the 2, and 3, negative 5, 9. And then because there's an equals here, it's pretty common to draw a line there. And that is what makes it an augmented matrix, is that we're putting a line there in the middle to separate between the coefficients and the equality. So in order to use the matrix to help solve the system, we want to multiply the equation. We want to get this matrix so that there are ones along the diagonal and zeros underneath them. So for example, I don't want, this is already a 1, so that's great, but I don't want this to be a 3. I want this 3 to be a 0. And there'll be a lot more instructions on that as we move through this unit. But in order to make that happen, I know that if I take I can replace this row 2 is going to be replaced with negative 3 times row 1 plus row 2. That's using this step here. Replace a row by the sum of that row and a constant multiple of some other row. So I'm going to take my entries that are currently in row 1, multiply them by negative 3 in my head, and add row 2 to them, and then write the result down here. So picture taking 1 and multiplying it by negative 3, which would make it negative 3, and then adding 3 to it, which will make this be 0. Then I'm going to take negative 2 and multiply it by negative 3, which is 6, and I'm going to add negative 5 to it, which makes it 1, which is fantastic that that came out to be a 1. And then I'm going to take the 2 in row 1, that'll make it negative 6, and then add 9. So negative 6 plus 9 is 3. So this, when you have ones on the diagonal and zeros underneath, is called row echelon form. That's supposed to be an E. Row echelon form. And that's pretty good, because just from there you can already tell that this is 1y is equal to 3. And so then you can use back substitution to solve for the other variable, because x plus 2 times y is equal to 2. So x minus 6 is equal to 2, so x equals 8. So that's kind of using a combination of matrices to solve a system. We're going to go ahead and keep going here and try to solve the rest of it to what's called reduced row echelon form. So I'm going to take where we left off here and do another row operation here, and I'm going to say that this row 1 is going to equal 2 times row 2 plus row 1. So I'm going to leave this one, 0, 1, 3, but this row is going to get 2 times row 2 added to row 1. So 2 times 0 is 0 plus 1. 2 times 1 is 2. Plus negative 2 is 0, and 2 times 2 is 4. No, 2 times 3 is 6, plus 2 is 8. And then this is called reduced row echelon form, and then you can see that x is equal to 8 and y is equal to 3. And that is why matrices are so helpful. And the reason that we really like to do the work of solving a system in a matrix is not because a 2 by 2 system is so hard. It's that a 3 by 3 or a 4 by 4 are really hard. And you can teach a computer to figure out what to do with these things. And so a computer can solve a system by changing it to reduced row echelon form. And then you never have to do this yourself, but you got to learn it to understand the background of it so that you can solve problems that involve matrices and other situations. So more on that later. Thanks for watching, and